Hello, this video is an introduction to the analysis module of the MDAnalysis library. This module contains various submodules with classes and functions for the analysis of structures in molecular dynamics trajectories. The analysis module has both common algorithms like the RMSD, RMSF, RDF, and also it has some specific to MDAnalysis library unique algorithms. For example, you can analyze the similarity of passes of two different molecular dynamics trajectories. This video is aimed to give you a basic introduction to the RMSD calculations with MDAnalysis library. Even if you are new in structural bioinformatics, you may notice a certain similarity in formulas of root mean squared deviation and the standard deviation from statistics. The difference between them lies in what they measure. The standard deviation measures the spread of your values around the mean value of your dataset, and the root mean squared deviation measures the deviation of your atomic positions at some specific time point from the atomic positions in reference structure. However, it is more complicated than that because you need to remove noise due to diffusion and in general spatial displacement of your atoms due to molecular dynamics. And this is exactly what the second formula does. So besides just calculating the root mean squared deviation, you also perform rotational and translational alignment of your atoms at a specific time point to atoms in the reference structure. You will typically use backbone or C-alpha atoms for RMSD calculations because you are interested in the overall conformational motion of the protein structure. And side chains of amino acid residues, they introduce noise due to their rotation. Also, RMSD is often weighted by masses of atoms used in the analysis to account for different masses of different elements, which kind of makes it more precise in representing the overall conformational motion. As with any Python script, you generally start with importing different Python packages and their modules. I will copy-paste most of them from the previous test code, and then I will add specific modules for RMSD analysis. All the RMSD-related code is currently stored in the RMS submodule of analysis module. I will also mute the deprecation warnings and start with creating the instance of universe class with test topologies and trajectories. Next, I will instantiate the RMSD class from RMS submodule. You first pass the mandatory argument, which is your universe, and then you can also add different key vargs specifying exactly the kind of RMSD calculations you want to perform. Next, you call the run method of your RMSD instance, and after that you collect the results. Here I run RMSD calculation for the backbone atoms of my test structure using the first frame of trajectory as a reference frame, which is the default behavior of RMSD class of MDAnalysis. The output contains two-dimensional MD array of the NumPy library with first column corresponding to the indexes of frames, second column to the time points, and third column to the actual RMSD values. And now we can plot our results, and as I have already shown you how to plot stuff with a quick interface of the matplotlib in a previous video, I will focus on the RMSD. So generally, RMSD is a great metric to start your analysis, but it is certainly a bad metric to finish it. You should never make any conclusions based on the RMSD alone, as it is often called the degenerative metric. In molecular dynamics field, you deal with three-dimensional coordinates of our systems, and what RMSD does is it basically collapses these three dimensions into one dimension. So you can easily plot it with respect to time, for example, but it does not represent precisely your particular conformation at a particular time point. One of the consequences of such dimensionality reduction is that one RMSD value can correspond to multiple three-dimensional conformations of your protein. It can give you a global view on what is going on in your trajectory, like your protein reaching equilibrium state, but usually you need to contemplate such indicators with other metrics to prove something. And here is our RMSD curve. Obviously, it is a tiny little interval of only 100 picoseconds, which is shipped with MDAnalysis tests, additional package to MDAnalysis library. And in the future videos, I will show you how to load your actual trajectories and topologies into MDAnalysis library. To plot RMSD as a function of time instead of as a function of frame indexes, you just change the column from 0 to 1 in your ND array in the plotting function. RMSD calculations by default are unweighted, so to make them weighted, you need to specify it as an additional keyword argument in the RMSD class during its creation. There are also multiple other settings and ways to perform RMSD calculations. For example, you can compare two trajectories pairwise instead just of analyzing one trajectory, and in the future videos I will cover it. As for this video, we are done. Thank you for your time. Let me know if you had any trouble or if you have any questions.